Okay, welcome back. We literally have 3 weeks left of class, right? This week, we get a week off, and then we have 2 more weeks, and then finals week, right? So 3 weeks of class, 3 out of 15, right? We're almost to the end. We have 20% left. So we are in the midst of talking about beam deflections, right, and slopes. And we've gone through some examples of some, going through some integration, essentially starting out with an overall free body diagram, getting our external forces. We can then use that to cut our member, right, and do an internal force free body diagram to develop an equation for the internal forces. A lot of times we develop it for moment. Right? Once we have an equation for the moment as we go along the length of the beam, we essentially have this relationship between moment and deflection, being the second derivative of deflection with respect to the distance along the length. We can integrate that thing twice. We use the powers rule and the constant rule of rules of integration. Right? That's like 99% of what we've been using. So we end up with some constants. We evaluate those constants by using boundary conditions. We have to be careful. Here's Olivia. The recorded lecture is now going to be available. You are number 30. And so we use boundary conditions to evaluate those constants. We have to be careful, though, that those boundary conditions lie within our range of the equation that we developed for the moment. That was this example that we just did on Friday. And so those boundary conditions are used to evaluate those constants. Then we can simplify. Okay, no real rhyme or reason to the simplification. We just try and simplify, okay? Get it to something that's easy to use, and we'll have slope and deflection, right? Which is slope and deflection as it relates to loading, dimensions of our member, right? Length, where we're at in a member. Deflection is going to change as we go along the length of our member. And then we use those equations to then evaluate the slope or deflection at any point along the beam, okay? Then I started talking about this idea of superposition, right? We can combine the effects of different situations to come up with a solution for a situation of interest based on splitting up our problem into 2 maybe problems that are already predetermined, right? We have charts out there. I'll show you here in a little bit, okay? That solutions for general problems have already been conducted. So if we wanted to look at the solution for a point load at the center of a simply supported beam that also has a uniform load on it, we can break that up into just looking at a simply supported beam with a uniform load. We're going to add to that a simply supported beam with a point load at the center. Okay. Some assumptions that we have to make, though, is that the stress-strain relationship is linear. So going back to our radius of curvature derivation, right, with our stress, my over I, negative my over I. Same thing holds true, right? So the stress in our cross section is linear as we make our way from our neutral axis, right? For the location that has 0 strain, which is 0 stress, outward. We have a linear relationship to stress and strain. Deflections. Are small relative to span. Right, that was my little noodle thing. Like this noodle. Right, we're looking at deflections that might look like this. We can't look at deflections that look something like this, right? Okay, shit gets weird when you start getting stuff like that. So, deflections have to be small relative to the span. Boundary conditions in each case are the same as original problem. What does that mean? Well, when we took this case where we have the point load and the uniform load, we break it into 2 problems. Each of these problems are simply supported, right? So the boundary conditions for each of these are the same as the original. And that has to hold true to make sure that we can use superposition. The other thing is loading variables. Do not exceed first order. I just mean loading is either linear or constant. Right, so we can have point loads, we can have uniform loads, either uniform loads that are constant or uniform loads that are linear, right? First order. Loading that changes with respect to x, but not with respect to x squared, right? All right, let's do an example. It's a lovely guy right here. All right, we have a steel beam, modulus of elasticity of 200 gigapascals, moment of inertia of 129 times 10 to the 6th millimeters to the 4th. That means a whole lot to everyone out there, I know. Right, pretty decent sized beam. It's shown in the figure, and they want us to determine the following. What is the reactions at A and C, right? AY and CY. In terms of the variables, right? We're not going to put any numbers in here just yet. We want us to determine the equation for the moment between A and L over 2, as seen in the figure. Okay, so that's nothing new, right? Continuing down our path of determining our deflections. We want to state the known boundary conditions at L and L over 2, or at A and L over 2. So what's going on? What do we know about this setup at A and B? And then they want us to use the method of integration or double integration method to determine the equations for slope and deflection. Right? Double integration method essentially is saying we're going to integrate twice because we're coming up with an equation for the moment. Right? Triple integration method would be we would come up with the equation for the shear in the beam. Okay? We're going to come up with the moment. So we're going to use the double integration method to determine the equation for the slope and deflection. And then we're going to come back at the very end. We're going to relate this, what we develop here, to a method that we could have used based on superposition, okay? Anybody remember the first step here? Damn, nothing, just fucking crickets.
Hold on.
Not out of the first two rows. What? Here's the first two rows. Right, an overall free body diagram, right? Essentially half of it's done. And then on part of that, we needed to come up with the deflected shape, right? What do we think the deflected shape of this would look like? Yeah, do something like this maybe? A U. A U. Right? So then based on this, right, global free body diagram, the step is to create a free body diagram, assume a deflected shape, and then determine our reactions, right? We have to determine all of our external forces so that then we can cut it again, right? That would be the next step, cutting it again so we can get an internal force. So we're gonna say we've got some of the forces in the x direction equals 0, right? Well, x is along the length. We have a pin at A, so there would be some sort of reaction at A, right, in the horizontal sense, or could be. Something that forces about the 0, well, that essentially tells us that AX equals 0. No other forces applied in that direction. Sum of the moments about A equals 0. We've got three equations. And three unknowns looking at this, right? This is determinant. Right, three equations. There are three unknowns. We got AX, AY, and CY. We went through our first equation of equilibrium, some of the forces in the x. Second one, some of the moments. I'm assuming I am choosing to sum the moments about point A. You could choose to sum the moments about point B, point C. You could do L over 4, right? It does not matter. You just need to sum the moments somewhere. That's your equation you get. I'm going to sum the moments about A because when a force has no moment arm, right, it's not going to be a part of this equation. And so if I sum moments about A, AY goes away, and the only parts of that equation are known loading and this reaction over here that we don't know. So essentially gives me a method for calculating CY. So we've got, holy shit, we've got a lot here, right? So we've got our point load, right-hand rule about A, it's twisting to the right, fingers pointing into the page, so it's negative. We have our point load P times its moment arm, well, that's L over 2, the distance from A to B. We have our uniform load. Well, our uniform load is going to have a resultant. And that resultant is going to be the magnitude of our entire uniform load, which would be the uniform load times the length over which it acts. So W times L. Okay. And it's acting at the centroid of our uniform load. If this was a linearly changing uniform load from, say, A to C, it'd be at 2/3 the distance from 0, right? We have a constant uniform load, so we have a constant WL. Its moment arm, again, it's acting, the centroid, the resultant of this uniform load acts at the center of the beam. So that has a moment arm of L over 2. So we get this, and it's acting in the negative moment direction, right? Right-hand rule into the page. Then we have our reaction at C, right-hand rule, it's going to be positive, so CY times L. Based on this, we can get an equation for CY, right? Just rearranging. It's essentially half the resultant of the uniform load plus half of the point load. Makes sense? Looking at symmetry here, I assume that would make sense. Or if you pull the half out, it'd be half times WL plus P. We've got another equation of equilibrium, right? Because we still have one more unknown. Some of the forces in the Y equals 0. Well, P is acting in the negative direction. We've got this resultant of the uniform load, which is WL. We've got our reaction at A plus our reaction at C. Based on this, AY equals CY equals all that stuff up above, right? Essentially plug in CY into here, we get AY equal to CY equals that same amount. Any questions? None? 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 None. Well, that would be our reactions AY and CY in terms of the illustrated variables. Okay. Now they asked us to determine the equation for the moment between A and L over 2 as seen in the figure. So we're trying to figure out the moment that's inside the beam between 2 points. We need to cut the beam between those 2 points. So we're going to draw a free body diagram. Cutting our beam at some arbitrary distance from A. We were told we wanted an equation between A and B, right, the midspan. So we impose our internal forces, right? We're going to have an internal shear. This is positive, up on the left, down on the right. Positive moment. We have our uniform load that's going to be acting. We don't have a point load because we're not past L over 2 yet. And we have this applied reaction at A. So if we sum moments about this cut, AA, we know that that has to equal 0. Well, about this cut, we have mx. Right? We have this internal moment acting at that cut. Assuming it's positive, so it's positive. Then we have our reaction. Well, our reaction is acting upward. Its moment arm is the distance x that the cut is away from it. So that's going to be negative, right? Right-hand rule, thumb's going into the page. So we have a negative force times moment arm, AYX. Then we have this uniform load. That uniform load is going to have a resultant. Which is going to be the uniform load magnitude times the length over which the uniform load acts, right? So it'd be WX. And that resultant is going to act at the centroid, which is going to be half that distance, x, right? So, looking at the right-hand rule, if we have a force that's acting downward, spinning a moment about this cut AA, right-hand rule, thumb sticking out of the page, it's positive. So we have positive. The reaction, or our force, is W times X. And the moment arm at which that force acts is going to be half whatever distance we're using to cut the beam out, right? Well, we know AY and CY now as a term as it relates to our variables. The uniform load magnitude, the length of our member, and our applied point load. So if we rearrange this for mx, we get 1/2 negative wx squared plus wlx plus px. Seem easy enough? Yes, so, maybe so. Well, same process we've done multiple times now, right? External forces and reactions, then cut our member, derive an equation for the moment as we work our way along the beam. Once we have this moment, we'll now we're going to use the method of double integration, but before we do that, they said for part C, they say we'll state known boundary conditions at A and L over 2. So if we go to part C, they want boundary conditions, right? BC. If we look at A, right, at this point, x equals 0. Give me a boundary condition at A, somebody. What do we know about this beam at A? What is it going to do or not do? What's that? Yeah, B equals 0, right? It's not able to displace at all. It's pinned, it's fixed right there at A. So we'd say at x equal to 0, deflection equals 0. They also asked us for the boundary conditions at B, which is L over 2, right? At x equals L over 2. We had one similar to this on Friday.
Slope equals 0.
Slope equals 0, yep. Because we have symmetric loading, right? We guessed at what this deflected shape would be. Well, if we look at this deflected shape at B, right, that deflected shape has no rotation. Because it's symmetrically loaded, it's going to go down to a maximum at the center and then come right back up. And when it's at a maximum, it's going to have 0 slope, right? It's going to be still flat like it was at the very top, right? Unloaded. So we got dv dx equals 0, right? Or theta. So those are our boundary conditions at A and B. Part D, now we get to do all the fun stuff, right? We got to start integrating. So we do double integration to determine equations for both our slope and our deflection. We start with D here. Essentially, we know that, let me see, I change this up here. EI times the second derivative of deflection with respect to distance along the length is m. Right? Moment. Well, we have an equation for moment now. We're going to plug that in. So now we get, and I'm going to multiply out the half, so we get negative wx squared over 2 plus wlx over 2 plus px over 2. Now we integrate. We're heading for an equation that has v and dv dx. Right? We have dv squared dx squared. So we're going to integrate the first time and get an equation here that's EI dv, whoops, that was dv dx equals, what's the first term? Yeah. Right, Powers rule. Wx squared over 2. Powers rule tells us that we take whatever power we have, we add 1 to it, so now this x becomes x to the third, and then we have to divide by that, whatever that integer is, right? So if it turns into a 3, we're going to divide by 3. Well, if we divide by 3 and we already have a half, we're going to do 2 times 3, we're going to get 6. We get wx cubed over 6 plus WLX squared over 4, right? Again, power rule. We have x to the first power. It's going to become x squared. We're going to divide by the 2 term now because we have x squared. 2 times 2 is 4. We get WLX squared over 4. Same thing happens with px over 2. And as always, when we integrate, we get a constant of integration. I am going to, miserable. Okay. I'm going to jump ahead and just say, well, now we have an equation for slope, right? dv dx. Well, we have a boundary condition for slope. dv dx is 0 when x is L over 2. So I'm not going to integrate again just yet to get our deflection equation. I'm going to say at x equal to L over 2, we know that the slope, or dv dx, equals 0. And if I have this boundary condition for slope, then I'm going to be able to evaluate this equation and figure out exactly what C1 is. Okay, C1. Well, I guess we can enter this whole thing in. So we've got EI times 0 equals negative W L over 2 cubed over 6 plus WL times L over 2 squared over 4 plus P times L over 2 squared over 4 plus C1. I'm not going to bore you with all of the details to get here, but I'm going to tell you that you're going to come out with WL cubed over, 24 minus PL squared over 16. So out of that whole mess, right, effectively we get 0 equals this big mess. We multiply all of this out, we simplify it, we'll end up with a WL cubed over 24 and a PL squared over 16, and the signs remain negative. No. No. Why? I don't get that. Fuck. I can't let this go. I found an error. Anybody see an error here? No? Yeah, there should. And I think it should be this one. Right? That makes sense.
Sure.
What do you mean, sure? This whole thing right here.
I know, but you subtract the PL to the other side.
Oh, yes, you do. And then that's how that, okay. So they're both negative then. Thank you. See?
Yeah, but why-
I need help just as much as anybody.
Why is the one on the left negative?
Because the WL, this term dominates this guy.
Gotcha.
So when you take these two to the other side, this is greater than this, so this stays negative.
Okay. And then that PL squared over
It's
6.
just this, slide to the other side.
Right, but that's supposed to be negative, right?
Oh, yeah.
Okay.
Yep, it is supposed to be negative. Whew. Trick question. This was a learning exercise. You guys succeeded. Yeah.
Okay, so you find a common denominator for the first two, combine them, and then move them over.
We sure did.
Okay. So what's
I have it all written out here, but I skipped it in the hope of that we would move through this faster than we did. Okay? Probably would have been better off just doing it that way. All right. So now that we've evaluated C1, well, now we can plug C1 back into our slope equation. And what did you just say to me? You did? You know how we got there? Shit. You sure will. It'll be on your own time, not mine. What? What do you mean don't you get? What don't you get here? How this is, you don't get the signs? Do you get that? You're killing me now. Here we go. I'll show you this. This is how we got to this. Okay? So if we plug in x equal to L over 2, the slope equal to 0, you end up evaluating this whole thing, and you end up with this equation right here. Right? This is everything multiplied out. Then from there, I essentially multiplied this by 3 so that we get a common denominator. Right? Again, as we mentioned, as we figured out, this guy dominates the equation. So we end up with 2 WL to the third, right? Negative. Because I pulled everything to the other side. Right? Pulled C1. C1 stays here. Pulled each one of these to the other side so the signs swap. So we have a higher negative. We have 3 times as much. So we end up with 2. Divide that by 2, we get 24. So then this is how we got to there. Does that make more sense now? If you need it again, Olivia's got it on her phone.
Oh, no, yeah, there you go.
Okay. All right. Well, you wouldn't have captured that on your thing anyway, so, or on the iPad anyway. Okay. Now we're all square, twice as long as I thought it would. So we have this original equation for EI, dV, dx, all of this mess here. So if we bring that down, we've got negative wx cubed over 6 plus WLX squared over 4 plus PX squared over 4 plus this C1, okay? That's what we established based on our first integration. Well, now we need to integrate again. We're gonna integrate all of these terms. I'm not gonna plug in C1 just yet. What's that? I will.
No, I mean, like, is it okay if we were to, like, plug in...
Oh, for sure. Yep, you sure could. Boom, just like that. Just crush this integration, right? Wx cubed over 6, well now it's Wx to the 4th over 24, right? 4th power, 6 times 4 is 24. Lx squared, 3rd power, 4 times 3 is 12. Px cubed, 4th power, x squared to the 3rd. Sorry, I started here and I was integrating again. Just get so excited, I just want to keep integrating, okay? Px cubed over 12. And then you have our constant C1. Well, that's constant of integration. We just add x to it, right? And all the while, when we do an integration, we always have another constant, so we get C2 out of that. We have these boundary conditions at x equal to 0, right? We decided the slope or the deflection was 0. We had a pin connection at A. Right? This is at A. We can use this boundary condition because our equation for the moment that we derive is in this segment of our beam. So that's the boundary condition we can use. So we'll say EI, the zeros are the best. Because there is an x in every one of these terms, and the x we're looking at is 0. Displacement is 0. So essentially we get 0 is the second constant of integration, or C2. Right, C2 equals 0. That's easy. So now our equation becomes negative Wx to the 4th over 24 plus WLX cubed over 12 plus PX cubed over 12 plus, well, now we need our C1 term. C1 is 2WL cubed over 48. It'll make sense why I brought the 2 over 48 back. PL squared over 16 times x. If we simplify this, we can pull out the Wx over 24 EI. We can multiply that by x cubed minus 2x squared plus L cubed minus px over 48 EI times 3L squared minus 4x squared. If you couldn't see that simplification in there, you have problems. Just kidding. I could never see that. The reason why I'm doing this is just, you'll find out in a second, okay? Just like freak out. I want everything to look just like this. So, going through that whole derivation, we integrated twice, found our boundary conditions, evaluated our constants, made some free body diagrams, right? 2 of them, evaluated our reactions, and we figured out what is the deflection of a simply supported beam with a uniform load and a point load at the midspan as we move from x to L over 2, right? X equals 0 to L over 2. This would be the equation. So it's like a crazy group of stuff, right? Well, if we decided to use superposition, right? Stress-strain relationship is 0 in this case, yes. Deflections are small, yes. Boundary condition in each case are the same as the original problem. Well, we can do that by looking at, right? We could look at the uniform load, and then we could look at a point load. And our loading variables do not exceed first order, right? We have a constant uniform load, and then we have a point load. So we'd be looking for, if we broke this up into 2 different cases, the way I would look at it for superposition is to look at a uniform load, simply supported. I'm going to add to that a uniform or a simply supported beam with a point load at the center. And why do I break it up like that? Well, out on D2L, I uploaded it. It's also in Appendix C in the text, and the ones on D2L I put out there are from my mechanics textbook, which are a little bit different, but essentially the same thing. And they have, because we're engineers and we're lazy, okay, all of this shit is tabulated for us already for general loading scenarios, okay? Right? A simply supported beam with a uniform load, that's a very common loading scenario. Simply supported beam with a point load at the center, common loading scenario. So then we start complicating things. Well, we can essentially just add up these uncomplicated things, or the things that are already have packaged solutions for. So these are the ones that are out on D2L. These are from my mechanics book, okay? But You go to appendix C, you'll have one as well. Okay. Well, if we look at displacement, right, and then they have v prime, well, v prime is slope, right, or the first derivative. So if you look at displacement for our point load, this guy here, and displacement for a uniform load, simply supported beam, we get these two things. Well, if we look back up above, look at that. You guys derived it. This guy here, same as the first term, right? Point load, same as the second term. And that's why I simplified it. It's kind of hard to see that that came out of this equation up above that.
Looks like Q.
Effectively the same thing.
That's below the uniform load. What's the Q?
That's like
Q is
W.
W.
Oh, that's the W.
Oh, yeah,
I
sorry.
just didn't read where it said, I just assumed it.
Yeah, sorry, variable wise. Q is the uniform. So you can see how superposition can be very powerful. You don't have to go through and do double integration, evaluate constants and all this stuff, right? If we have the ability or the intuition to some level to look at a problem and break it into some more simplified parts, we're able to take those simplified parts and add them together and come up with a final solution, right? Same as going through this longhand method. So as I mentioned, D2L notes are also in Appendix C in your text. And as I mentioned, the D2L notes are from a different textbook, okay? What are we doing on time? Oh, sweet. Okay. So superposition gives us some pretty cool tools to evaluate things more easily. What also some of these package solutions do is they give us the ability to solve things directly, right? So if we had an example here for a beam, it's loaded as shown, so we have a concentrated moment. So simply supported beam with overhangs on each side. And on one end of the overhang, we have a concentrated moment of 150 kilonewton meters. Right? And they asked us to determine the beam deflection at point H. Assume that EI equals the modulus of elasticity times the moment of inertia is 8 times 10 to the 4th kilonewton meters squared. And it's constant. We need that to be constant, as we've talked before. So if we start our solution like we do with anything, right? We start with our sketch of our deflected shape is one of the bigger things. So I'm going to do this. I'm going to overlay it. So if we have a concentrated moment that's trying to torque the end of our beam, I would say it would do something like this, right? Where we would have our moment applied to the end of our member. That moment is going to torque up the end or the overhang of that beam. It's going to deflect and run off to the end.
Is it gonna be more torque where the moment is? So is that the deflection supposed to be like that nice line there?
Well, I mean, I probably botched this pretty hard, but
I was just curious.
no, that's fine. You can be critical of my art. Okay, we're gonna start over, all right? I mean, this is actually kind of important here, okay? You have a good point. I'm gonna draw a straight line. It should be a straight line from there. And then I think it does ish. Something like that, okay? It's a guess. But in general, anybody agree or disagree with this? Do you agree with this?
No, I have a question.
Oh, what's your question?
It's supposed to be more to the right though, right, the deflection, like the.
Yes.
Okay.
It should be more to the right. Yeah, because I mean, it all come back to applied loading. If we went and looked at, anyone want to give me what the moment diagram of this thing looks like? Positive concentrated moment. If we look back at our rules for moment diagrams, positive concentrated moment is a negative jump in moment, right? M equals negative M naught So here at the very end, we're gonna have a negative jump, so it's gonna come to 0, right? We have 0 moment in our moment diagram. It's gonna do something like this. We have no applied load or shear out there, right? No shear. It's gonna be constant. And then it's going to come back down to 0. Or just do something like that. That's our moment diagram. Anybody feel like this is not right? Speak now. This might not be right. I could be wrong. But I'm pretty sure that this is how it goes. Pretty sure. Give me 95% here. Right? It's constant. It's B. Well, we're gonna have some reactions, right? If you imagine somebody taking the end of that beam and twisting it, right? We're going to have some reaction at B and A in doing so. Those reactions are going to create shear. Shear is going to change our moment. It's going to come back to 0. That's why when you look at the deflection, right, our maximum deflection is going to be over here where we have dominated by this moment that's going to induce deflections in our member. Okay. Whew. Man, I made it past that, huh? They want us to figure out what is the deflection way out here at point H. Well, if we're trying to get to a deflection at point H, how I'm going to get there is by looking at the slope, right? By looking at the moment diagram and the deflected shape. Right? This is a straight line. We have no applied forces out here. Right? Our moment is 0. Shear's out here is 0. No applied forces. So this is a straight line. When this thing deflects, it's going to start at A and it's going to work just straight out at whatever slope it's at. Well, we know that that slope times our length gives us a displacement, right? Right? Rise over run, the slope is the rise over the run. So rise over run times the run equals the rise. Okay? So that's where we're headed. Well, if we go back and we use the method of, well, in some sort, superposition, but really just prepackaged solutions. So out here again, out on, this is a shitty copy, isn't it? If we go out to D2L or Appendix C in the text, you're going to find prepackaged solutions. Okay? One of those prepackaged solutions is a simply supported beam with a concentrated moment at one support. Effectively what we have. You look at what's going on here, right? Constant moment back to our support at B. Effectively we'll have this going on. If ultimately we're trying to figure out slope at A, we really want the slope at the opposite end of our member from where the moment is applied. So if we go back to this prepackaged solution, they give us theta A, theta B. Kind of hard to decide what's what here, but this is A and this is B. As you can imagine, as we've seen here, what am I doing? Can't write a B, okay? Theta B from our sketch even looks more than theta A. Makes sense based on the loading. Well, if you look at this equation, unfortunately it's opposite from the way our problem statement is. Theta A is the side that the moment is applied. As you can imagine, the rotation at that point is more, right? 1/3 versus 1/6. It's twice as more of a rotation at the end with the moment on it than without. We're really interested in the moment, or the rotation at the end without. So we're going to say theta A equals m naught L over 6 EI. Yes.
So does it matter about the pin connection and the roller connection in regards to those equations?
Well, so like our problem has the same support conditions as the problem that we looked at in D2L.
Right.
So you wanna make sure
it's
that-
on the other side.
Yeah, but it's essentially just flipping this over, right? Yeah. Oh, you're saying that it's at the roller connection versus at the pin connection?
Yeah.
Yeah, it doesn't matter.
Okay.
So, based on D2L, right, these package solutions, I'm trying to explain how powerful some of this stuff, or how easy, what's the best word here? How great it is that there's engineers that came before you, right? And they are lazy, just as lazy as you are, okay? And so they come up with these solutions ahead of time to aid all of us, right? We can thank them for this, okay? And so sometimes the best method is to go through and evaluate what you think the behavior of the system is, and then go through and see if there is something out there that you can pull together to create the solution that you're looking for. Okay? In this case, I don't have to add this to a different one, but if we had a point load at the center, we could go back to the results for a point load at the center, right? And we could pull out some of those behaviors and solutions, right? We can add those things together. So we're really interested, again, as a deflection at H. We've decided that that's going to be just the slope at H times the length of our cantilever. So we need to know what the slope is at that cantilever. Well, we know it's m naught L over 6 EI. Well, we know m naught is 150 kilonewton meters. Our length is 8 meters, and EI, we were told, was 8 times 10 to the 4th kilonewton meters squared.
Why do you only use 8 meters as your length and not the full length of the beam from the moment to the point H?
Oh, to evaluate theta?
Yeah.
Because that is the length in which the solution relates to, right? It's relating to this beam member,
Okay,
which is spanning between our supports.
gotcha.
Right? And as we mentioned before, this cantilever is just an added extra. There's no applied load out there. So it's really just going along for the ride, right? When it rotates on the other side of the support, it has to rotate on the left side of the support. It'd get a bit different if we had, say, a point load at the end out there, right? But for this case, when we're trying to figure out theta A on the right-hand side, that is based on the length between our two supports. So if we really draw this, whoops. Wow, that's so cool. All right, we're calculating theta A. Well, theta A is going to be the same on both sides. Complementary angles. 2 o'clock, damn it. And we know that our deflections, based on knowing the slope, is just the slope. We have no applied loads, so this member is going to maintain a straight section, right? It doesn't bend because there's no applied forces. We can then say that the displacement at H is essentially the slope times the length, right? This is L. And we'll finish that up on Wednesday.